Hey everyone, and welcome to this explainer. I'm absolutely thrilled you're tuning in today because we're going to do something pretty incredible. We're going to decipher a secret, hidden language. It's a language spoken all over the world, but it's rarely understood by the general public. We're talking about the complex, highly specific visual alphabet that keeps massive, high-speed rail networks operating safely and efficiently every single day. So let's dive right in.
Really think about it for a second. Have you ever wondered how a train driver, who is piloting thousands of tons of steel at incredibly high speeds, knows exactly what lies miles ahead on the track? They can't exactly just slam on the brakes like you would in a car, right? The margin for error is literally zero. The answer lies in this highly structured flow of information. It translates physical environments into symbols and then presents those symbols flawlessly to both the engineers building the railway and the drivers navigating it.
When you look at a genuine training diagram like this one from the West Midlands Projects Group, it outlines an introduction to plan symbols. Now, to the untrained eye, sure, it just looks like a chaotic mix of lines, circles, and bizarre geometric shapes. But by the end of our time together today, this explainer is actually going to act as your personal decoder ring. We're going to break down this fascinating esoteric alphabet step by step.
Okay, let's kick things off with Section 1, the master blueprint and the checklist.
So, before anyone even thinks about drawing a single signal or a switch, they've got to create what's called an engineering scale plan, or ESP for short. As defined by railway engineering departments, the ESP is the foundational basis for the yard layout of an entire station and its signaling plan. The absolutely crucial takeaway here is that this isn't just some rough sketch. It is the high-stakes master blueprint for all physical rail infrastructure in a given area. Literally everything else derives from this single document.
Now, because the stakes are so astronomically high, creating an ESP requires intense administrative exactness. In fact, the Indian Rail Ministry uses a really fascinating phrase for this. They state that these plans demand, quote, religious scrutiny. It's a heavy choice of words, isn't it? They note that if this religious scrutiny is done properly at the divisional level, dangerous errors are completely prevented and massive amounts of time are saved. There is zero room for approximation here.
To actually enforce this religious scrutiny, there's a ridiculously strict checklist that has to be followed before the actual track drawing even begins. Just look at these requirements. The title block size, it must be exactly 170 millimeters by 65 millimeters. The spelling of station names must be totally exact, pegged to a precise kilometer and chainage marker that shows exactly where the center line of the station building sits. Every single line has to have a clear designation for up and down traffic. Oh, and you must map out the nearest junctions and block section lengths. It is a rigid, bureaucratic grammar designed to ensure absolute clarity. Because out here, a typo doesn't just mean a quick eraser correction. It could literally mean a collision.
Moving right along to Section 2, a standardized alphabet, specifically the British Standards Institution 376.
We're relying on the British Standard Training Manual, specifically BS 376. And you might be wondering, why is this so critical? Well, from the very early days of railway signalling, it became terrifyingly clear that if the design staff sitting in a warm office and the installation staff out working in the dirt didn't speak the exact same visual language, trains would crash. BS 376 ensures that a specific triangle or a specific dashed line means exactly the same thing to every single person touching the project.
All right, let's get into the fun stuff. Section 3, deciphering the signals.
We'll start simple. Take a look at the strict proportions required when drawing physical semaphore arms. The standard dictates exact comparative sizes. Notice how the main arm is drawn exactly 3 units wide and 1 unit high, while the subsidiary arm right below it is distinctly smaller, capped at 2 units wide. Even the circles that represent light signals mandate that short-range signals be exactly 2/3 the size of long-range signals. This brilliant precision guarantees that no one misreads a primary stop signal for a secondary shunting instruction.
What's really fascinating here is seeing the evolution of technology captured entirely in simple line drawings. On one side, we've got the older mechanical ordinary signals. You can recognize them by those simple, solid flag-like arms used for stop and distant permissive signals. But contrast that with the power signals next to them. Do you see how the arm is partially filled or altered? Just by tweaking the geometry of the symbol, the plan is telling the engineer, hey, this signal isn't pulled by a human lever and a wire, it is fully powered.
And as tech progressed, so did the symbols. Enter the color light signals. So instead of physical mechanical arms swinging around, we have circles representing light aspects. On one hand, you see the 2 and 3 aspect multi-units, basically your combinations of red, yellow, and green. But then, look at the 4 aspect multi-unit. By stacking 4 circles vertically, the visual sentence expands. Adding that extra aspect allows the signal to tell the driver not just to stop or go, but to expect a very specific sequence of signals ahead. It adds this critical layer of meaning that is absolutely essential for high-speed braking.
But wait, what happens if the track splits? We can't just tell the driver to go, we have to tell them exactly where they're going. And this brilliantly illustrates the solution, the junction indicator. Check out those angled circles stemming off the top of the main signal post. In the real world, these visually represent a row of white lights that angle to the left or right, confirming to the driver that the track switches ahead are safely locked into the correct intersecting path.
Now, it's definitely not all high-tech lights. These plans are literally littered with highly specific, kind of oddly named historical components. For instance, look at symbol number 45, the fireman's plunger. It's this wonderful relic of the steam era. It was a physical plunger that a locomotive fireman would use to alert the signal box of their train's presence. And just below it, symbol 46, you've got the ground telephone. That was a literal lifeline, allowing a stranded driver to speak directly to the signalman.
Which brings us to Section 4, Tracks and Switches. You see, tracks aren't just static metal lines. They actually move, and the symbols have to show exactly how they move. First, we see standard points, the switches that guide a train from one track to another, like simple handward points and spring points. But then there's a fascinating safety mechanism, trap points, shown with those little guardrails. Trap points are literally designed to intentionally derail runaway train cars. They guide an out-of-control wagon right into the dirt. They are sacrificing a wagon to protect a high-speed passenger train running on the main line. It's intense, but incredibly clever. And as yard layouts get tighter, the geometry, it gets wilder. Just look at these track crossing symbols, the movable switch diamonds and the single and double slips. Let me tell you, these aren't just simple X's on a map. These symbols dictate incredibly intricate mechanical intersections where rails physically shift within a diamond shape, allowing trains to seamlessly cross over each other's paths in highly congested station environments. One wrongly drawn line here, just one, and the installation team builds a junction that trains simply cannot navigate. Now, beyond the physical steel, we've got the hidden electrical language of the rails. I mean, how does the signaling system actually know where the train is? Well, those dashed lines represent track circuits. The steel rails themselves carry a low-voltage electrical current that the train's metal wheels short out, definitively proving its location. And right below that are axle counters, magnetic treadles bolted to the rail that literally count every single wheel passing in and out of a section. They track a train's exact location down to the millisecond. All right, final stop. Section 5, the language of safety. The real beauty of this entire system is how it takes the chaotic, physical world and translates it into an unambiguous, unbreakable chain of human safety. Just look at how seamlessly the environment itself is integrated. A towering brick viaduct, a deep tunnel cutting through a mountain, a road bridge passing overhead, all of these massive, complex engineering marvels are reduced to incredibly clean, simple, dashed and solid lines. When you combine that with the religious scrutiny of the engineering scale plan checklist we talked about earlier, this standardized alphabet ensures that absolutely nothing is ever left to chance. So, there you have it. We've decoded the master blueprint, translated the multi-aspect signals, and charted the track circuits and trap points. The secret language isn't so secret anymore, is it? Which leaves me with one final thought for you to ponder. Next time you take a seat, sip your coffee, and gaze out a train window on your morning commute, how many of these hidden symbols will you be able to spot flashing by? Thanks so much for joining me